Okay, so today we're talking t-tests. I probably that excitement I just showed was probably overselling it. But this is again, this is at this point we're almost at the point where I've taken up everything that you've done in 2126. So that's what we're doing again today. But again today we're looking at this from the angle of why do t-tests work? How do they work? That kind of thing. Okay. Alexa, turn on desk lamp. That's better. Let's kill that. Okay, that's not bad. Anyway, that's the way it's going to be. So I'm going to talk about t-tests today. Right. So remember to find the probability of a given value of a variable. We just talked about this last time, last class. And the variable is normally distributed. We turn something into a z-score, that's this here, and then we look up the probability in a z-table, and it literally tells us the probability because, as I mentioned last time, some poor bugger did the calculus for us. Thank you. That's very kind of you to have done calculus for us. Now, as interesting as this is, and I'm using interesting obviously sarcastically here, we're usually dealing with means, not with individual values. And I mean, I mentioned this in that lecture. I said, no one ever asks how many people have an IQs between 95 and 107. It's not a research question. It's a statistics practice question in an intro stats class. So to show that you know how to look things up in a Z table, it is not actually a very good research question. In fact, I don't even know it's a ridiculous research question. Most things in intro stats exercises are not really good research questions. They're just there to teach you how to use the formulas and use the tables and things like that. So we're usually dealing with means, right? Like, so is this group different from this group? Or is this group different from some theoretical mean, right? We don't deal with, or very rarely, do we deal with situations where we're dealing with individual scores, right? What's the probability of this? That's not something of an individual score. It's not usually something we're interested in. So instead of knowing about the distribution of X, we actually care about the distribution of X bar. That's the sampling distribution of the mean. That's all the possible values the mean can take. Okay. So I mentioned this vaguely or obliquely. I don't know. That's a good word, obliquely. I don't use that often enough. Maybe I'm probably because I'm quite possibly using it incorrectly at this point. The central limit theorem says given a population with a mean mu and a variance of sigma squared, the sampling distribution of the mean will have a mean mu, okay, of mu sub x bar equals mu. In other words, the sampling distribution of the mean's mean will be the same as the variable's population mean. And it'll have a variance of sigma squared divided by n. And as n increases, this distribution approaches normal, no matter what the shape of the parent population distribution. Note what I've bolded here. This is really cool that, in fact, this is the case. So no matter what the shape of the parent population distribution, this includes, by the way, if it was binary, if it was just a 0 and a 1. So a head or a tail. So we can count how many tails we have. A tails gets a 1, a heads gets a 0. You still get a normal distribution for the sampling distribution of the mean. It's wild, but I mentioned last time you can actually try this with dice, but you even better, just flip a freaking coin. Well, not everybody has coins. Everything's virtual. Last time I used cash. March of 2020. It's the last time I used cash to pay for anything. So maybe I don't have any coins. But if you flipped a coin 10 times and just gave 0 to heads and 1 to tails, on average, you're going to get a score of 5. Sometimes you get 4s. Sometimes you get 6s. This is one of those places where I could maybe draw a picture. I'll come back to that slide, but we can use this slide to draw on. So let's just set up some axes here. So our score here Sometimes we're going to get 5 heads. Sometimes we get 4 heads out of 10. We're going to count heads now. I said tails before. It wouldn't make a difference. I started saying heads, so I'm going to keep saying heads. Sometimes we'll get 6 heads. Sometimes we'll get, so that was 4. Sometimes we'll get 3. Sometimes we'll get 7. And I think you would agree with me that just intuitively, these should be equidistant from the mean, right? And sometimes we'll get, so that was 6, 7, 8. And sometimes we'll get 2, etc. And if you draw this, oh, look what you get, a normal distribution. Like you will get a normal distribution. It's wild. But so this is the sampling distribution of the mean of a variable that has 2 possible values, 0 and 1. Yet we get this beautiful curve like this. So intuitively, I think it makes sense if you just think about it like this, but it's also the case that mathematically it's true. So if you do the math, I got iPads everywhere. Okay, so if you do the math, my phone almost fell off here too. There's also a phone that I'm using. You find, in fact, that indeed it is the case that these things are all true. The math for this is just, there's a proof. I literally can't remember the proof. And I don't think it's important that I remember the proof because I could look it up if I wanted to. And I don't think it helps us a great deal. I think an intuitive understanding is important here. Okay. Now, so that's for the mean and the shape. This variance part here is a little weird, but think about this. So let's use this again. And I think if I write here, yeah, I can still write there. Now, it has a variance, whatever the variable is, it has a variance. If we had an infinite number, so this is the thing here, sigma squared over n. If we had an infinite number of observations, what would the mean always be? It would always be the same, wouldn't it? Because we're measuring the population, right? We're measuring the population. At that point, there shouldn't be the sampling distribution of the mean we should get a point. We wouldn't get a nice distribution that looks like that. We're just going to get a point because it's always the same. We're measuring the whole population because this is the limit as n approaches infinity. You may remember that from high school math. So as this quantity, sigma squared over n, gets infinitely large, this quantity itself becomes 0. In other words, we just get a point. We just get a point. We don't get a beautiful, pretty thing like this. We just get that. Okay. So again, you can do math that proves this. If you feel like looking it up, there's a Wikipedia page that's great and it's actually correct. So usually, sometimes a little vandalism, usually from frustrated statistics students, but this is something that even if we don't worry about the math behind it, I think intuitively it makes sense. And that's the beauty of this. Questions at this point? Okay. So the population distribution shape doesn't matter. We're always going to get a normal distribution if we're doing the sampling distribution of the mean. What matters is random sampling. So when I flip those coins, the point is that they're random events. They're independent random events. It doesn't matter as much as people think to the math. The math assumes random sampling. That's how this works. It's an assumption. You remember doing proofs of things in high school, and you would have to do, or university math, and you'd make assumptions at the beginning. One of the assumptions here is a simple random sample. It doesn't matter nearly as much as people think it does. It's not unimportant, but it isn't as important as people think. So to make the math work, even without random sampling, and this is done through simulation research, people found that it's pretty darned accurate. Like the central limit theorem is really robust. You can violate this assumption, this random sampling assumption. So to find out the probability of X bar, the probability of a given mean, we just use our old friend, the Z-score, right? So if we're looking at the likelihood of a mean being having a given probability, we are using x minus mu over sigma, but instead we're now interested in a mean. That's x bar. Central limit theorem tells me that this remains the same. Central limit theorem tells me that this is now this. So you may have been taught or may have thought that when you did a Z test of a mean, you have a different formula. You actually don't. It's the same formula. We start with this, and then the next thing we do is we sub this in, x bar in for x, and we sub sigma squared over square root of n, or sorry, sigma over square root of n for sigma. So it changes the formula in a way, but actually you're still starting from the same place. Okay. So let's work out a quick example of this. Let's go back with IQ. I have a thing, IQ is great because I know the standard deviation and the mean. So let's say 25 subjects, or I believe we're supposed to call them participants now, are given an IQ improvement course. So they've been sold a bill of goods. They have their IQs tested after the course. They end up with a mean of 110. Okay. So let's say we have a mean of 110. We got 25 subjects or participants or whatever the APA wants us to call them this week. Never understood why the word subject was pejorative, but that's because I'm old. Now we know that IQ in the population has a mean of 100 and a sigma of a standard deviation of 15. That's just a thing. That's just the way the world works. Okay, cool. So let's work this out. So we're going to do some pluses and takeaways, as I say here. So we got x bar minus mu over sigma divided by square root of n. 110 minus 100 divided by 15 over root 25. Notice how I've cooked these numbers, so the arithmetic's easy. 10 equals 15 over 5. 110 minus 100, 15 over 5. 10 over 3, 3.33. Wow, actually, maybe it worked. Probability of a z greater than 3.33 is less than 0.00043. Where did I get that? Well, I got that from my calculator, my old calculator that does some statistical functions. You could find the same thing at that web tool that I showed you last time. Frankly, your Z table in any Z table in any book doesn't go above 3. 3 is a really unlikely Z score. Oh my God, maybe the IQ improvement course works. No, but you probably could do something where you could teach directly to the test and get people to do better. But anyway, so you do this. Yes, we would say that this is very unlikely that the mean of 110 falls in the regular IQ distribution. Okay. There's a real problem here. And the problem is that we don't typically know sigma for the population. The reason we use Z all the time, IQ all the time, in statistics classes is because we know the population standard deviation. Because we being the humans, invented IQ tests, and we can design them such that they have a certain mean and standard deviation. I also don't know why I'm doing Shatner. They have a given mean of standard deviation, Mr. Spock. So we don't know sigma for the population. Well, wait a second. The expected value of S squared is sigma squared, right? Like this is S squared is an unbiased estimator of sigma squared. Standard deviation or variance. So the sample variance, that's this, right, is an unbiased estimator of the population variance. Yeah, good. Why don't we just sub S squared in for sigma squared? Okay, that's a good idea. That's a really good idea. Let's do that. The sampling distribution will change depending on we have two sampling distributions now. This is the thing. We get the sampling distribution of the mean, which we had before. Now we also have the sampling distribution of the variance. That's all the possible values the variance can take with a given n. Oh, that sounds like it's going to get complicated. So that sampling distribution now of the variance changes depending upon n, right? So the bigger n is, the smaller the sampling, the smaller the variance gets, because it's because of the central limit theorem. It tells us that. So we have to take that into account somehow. Things change depending upon n, the number of observations. They didn't change depending upon n with z. It's always the same table. We look it up. Z's don't change depending upon n. This will. So we can't use z. We can't use that. It won't work. When you get over maybe 30 subjects, it probably works. In fact, it worked. Yeah, 30. When you get infinity subjects, when you get over, it's so close when you get to say 50 or 60 that frankly, it's meaningless. But usually we don't have that luxury. And we want to be accurate. You want to have, Z would be a nice approximation, but it wouldn't be perfect. Okay. So we use something called T. This is the most basic T formula. It's X bar minus mu. In fact, doesn't it look exactly like the Z formula? Yes, it does. The only difference is we've put S here instead of sigma. We've simply replaced the sigma that's normally here in the Z formula with an S. We are estimating sigma with S. The rest of this is literally, Parks and Recreation, exactly the same. It's exactly the same. Huh. Cool. That's neat. Okay, why isn't this thing? Oh, I see it's doing this. Good. Things you have to remember here is that T changes depending upon the number of observations. The T distribution, the distribution of, we have the Z score, the Z distribution, it doesn't change depending on number of observations. T does. It changes by the number of degrees of freedom to estimate sigma squared. So by calculating S squared, we have lost a degree of freedom. The numbers don't have as much freedom to vary. Because when you calculate S squared, you have to fix a value. That value is the total, right? We did that when I talked about exploratory data analysis. So the value we fixed is it's the mean, which is also just a function of the total. So it's n times all the values. So it's the total, right? Not n times the number of values, n times the frequency of each value. Okay. Doesn't matter. It's the total. Okay, it's the mean, right? So it has to add up. All the numbers have to add up. It's a restriction. Remember that when I said, oh, they have to add up to, was it 65? And we had 5 values, and we could just pick the first 4. It didn't matter. But the 5th one was fixed. We've lost a degree of freedom because we want to get an unbiased estimate of sigma squared. Sigma. This is actually a pretty powerful technique when you think about it, because you don't have to know anything. You don't have to know anything about the population. You don't have to know its shape. You have to know its mean, but usually you know what you're comparing to. So let's say you want to say, is this group better than chance? And there's 2 alternatives. Well, the mean's 50%. For example, in that case, right? Questions so far? Okay. Now, what if we had pairs of observations? Wait, what have you done here? What is X bar sub D? Now let's zoom in on this a little bit, get an idea what's happening here. This is the mean difference between 2 pairs. Between 2 scores, between a pair. So let's say before and after. If you have before and after, you can create a new variable by taking after and subtracting before. You get the difference. That's the mean of the difference. And then if you have, that's the standard deviation of the difference. And this is the number of pairs of observations. When you think about this, actually, on top, really, that's x sub d minus mu. But what would we expect the average difference to be between two sets of observations if they're from the same population? we would expect it to be 0. So really, it's x bar sub d minus 0. So this is why people tend to go, yeah, it's just that. It's just x bar sub d, because it's actually minus 0. So why put it down? But it's actually something that, so what I'm trying to show you is it's literally, again, the same formula. So that's for pairs of observations. Move that over a bit. So again, pairs of observations or matching. So what you do in these cases is you match subjects on a variable. So you say, if you can use the same, let's say we're using heart, let's say it's a heart medication and it's going to control blood pressure. We're testing it. So we're going to, and you can't really do, you wouldn't want to do before and after in that case. Maybe what you want to do is you have 2 groups. So what you do is you measure everyone's blood pressure. And you find someone who has two people that have exactly the same blood pressure. I know nothing about blood pressure. It's just an example. So you take those 2 people, you give one person the drug and one person a placebo. And then the difference between drug versus placebo, we're going to call that one observation. So you've matched subjects. Usually you match them on the dependent variable. And you got to be darn careful what you're doing here, because now that you've matched people on a variable, they're now different on every other variable. So we should be really hopeful that they're the same. So you might do this with, another case you might do this with is, say, twins. So litter mates, basically. So let's say you had rats and you had litter mates. So you got to have rat 1 and rat 2. And later on in the course, we'll talk about, situations where you've got more than 2 matched subjects. So you've got like 4 of them or 5 of them. It's also weird to think that twins are actually, in humans, are just a litter of 2. It always strikes me odd. It's true, but it just strikes me odd. So in this case, we're just subtracting one score from the other, and we're doing x bar sub d, which is the difference between the 2, and technically we're subtracting 0. You'll sometimes see in a stats book with questions that are practice questions. You might even see it on a test from not me, because I wouldn't do this, but you might say the difference is assumed to be 3. No one ever does that. But in that case, it's trying to remind you that in this case, it would be x bar sub d minus 3. But it's never 3 or 6 or -4. It's 0. The mean difference we always expect is nothing if there's no effect of the treatment. So really, it's just x bar sub d. But again, it's not a different formula. All of these formulas are the same. And they all are descendants of Z. They're all descendants of Z. By the way, this distribution, the T distribution, was discovered by a guy named Gossett. And he worked at the Guinness Brewery in Dublin, Ireland. And he did, I think he did like quality control stuff for them. So he was looking at random sampling of Guinness, which, I mean, I've randomly sampled lots of Guinness over the years. It's like my dream job. It's like being a statistician in a brewery. Hello. But Gossett, when he published the Guinness Brewery, they had a lot of, I think they probably still do have a lot of in-house scientists. And they were cool with them publishing, but they didn't want them publishing under their own names, because if they publish under their own name, another brewery could snap them up, right? So they don't want to lose all their staff scientists and have them headhunted. So he published under the name Student. So you'll sometimes hear this called Student's T distribution. And it really should be called Gossett's T. And sometimes you'll see people call it Gossett's T. So he published under the name Student, just a student, which is pretty great. But his name was actually Gossett, Charles Gossett. And I think we should give him credit for what he did. So I don't call it Student's T. I'll call it Gossett's T, because Gossett did the work. It wasn't some guy named Student. He'd been a student at some point in his life. All right, questions on that? Okay. If your pairs aren't matched. Oh no. So what if your pairs aren't matched? What if you just have pairs? You just have scores. You have two. In fact, this is probably the most common, simplest. This is the most common, I think, research design we can think of. I cooked up an idea of just selecting some people and comparing them to a theoretical mean, like say 50% or 100 with IQ. In my career, I've done this once. I've done a one sample t-test. I've literally done it one time. I mean, I've done them like this. I mean, in anger, like, in battle, using them in a paper. So maybe you have two different populations. Maybe, we don't know. Well, let's test that. That's what we're going to be testing. So in this case, if you have two different groups, an experimental group and a control group, who you've randomly assigned to groups, right? Random assignment is really important, as you know from PSYC 2127. You have set up two different hypotheses, and the hypotheses here are HO is mu0 equals mu1. Okay. So in other words, or mu1 equals mu2. Mu2, by the way, my favorite band. So mu1 and mu2. Yeah, I'm doing it that way. So that means group 1 is the same as group 2. Alternative hypothesis, of course, or is mu sub 1 is not equal to mu2. They're not the same. Now we could use what's called a directional hypothesis and say mu1 is greater than mu2. But the more conservative hypothesis, and I'm not very conservative in a lot of ways, but I'm pretty conservative when it comes to science. And I think in this case, unless you have a very good reason to have what's called a directional hypothesis, you would have a non-directional one. Right. So maybe our IQ improvement thing, if we had something like that, and one group had the IQ improvement course and one group didn't, would you think the IQ improvement course could actually drop IQs? It seems unlikely. So maybe you could use directional there. I'd still use a non-directional test personally. When you're using a directional test, you better have a really good justification in my mind for doing it. And not just that doesn't fit with my theory, more like that's impossible. That's impossible. Me fail English? Yes, cultural references as fresh as when your parents were your age. All right. So the original T formula looks like this. It's the same one that I introduced a couple of slides ago. T equals x bar minus mu divided by s divided by the square root of n. Okay. And that is simply the statistic that we're interested in finding out about. That's the HO value, mu. And that's some measure of error. That's, in fact, this value, the standard deviation divided by the square root of the number of observations, it's called the standard error. It's just another measure of spread. So that's the error we're going to make. I point to this. I shouldn't be pointing to it with my pencil on my screen. This doesn't help you in the least. Okay. So what are we going to do with this? Well, let's figure this out. So now instead of having just one statistic, we've got two, x bar 1 minus x bar 2. That's okay. The null hypothesis is that mu1 equals mu2. Well, why don't we put those all on one side? Mu1 minus mu2 equals 0. Oh, look, and there's our null hypothesis. Now, so practically it becomes x bar sub 1 minus x bar sub 2. Because again, as we had with the repeated measures t-test, this is 0. The null hypothesis is never group 1 minus group 2 equals 7. It only is in stupid statistics problems. I've never seen it happen where someone's testing a hypothesis that is different than 0. Like the null is different than 0. I'm sure they exist outside of ridiculous statistics practice questions. I've just literally never seen them. And that's not a blind joke, because if it was, it would be offensive. I've never seen such a thing. Okay. And those of you who are listening to this, who aren't in my class and don't go to our university, or are watching this on YouTube and don't go to our university, I'm actually legally blind. I was making fun of myself. So don't protest outside my house about blind rights, because I lead that protest. Okay. I wouldn't want to get canceled. So Cancel culture. It's so horrible. So you see what I'm doing here? X bar 1 minus X bar 2 minus this thing here, mu1 minus mu2 is actually 0. So practically it's X bar 1 minus X bar 2. We got the numerator done. What's the denominator? Well, I just wrote the word error, so we have to figure that out. All right, well, let's figure that out. That's a thing we can do. We're smart. We're going to take the variances and we're going to add them together. You're saying, Dave, why don't we subtract them? Because you just don't. Let's just leave it at that, okay? So we're just going to add these together. But we have to weight them. We're going to weight them by the number of observations. This makes sense because the more observations you have, the smaller the variance gets. So we should really, basically it's a weighted average of these two variances. It's a weighted average of the two. And you don't add standard deviations, you add variances, then you take the standard deviation of that. So now our formula is this. X bar 1 minus X bar 2 over the square root of S squared sub 1 divided by N1 plus the square root, plus S squared sub 2 divided by N2. Then we take the square root of that whole quantity. That's this here. So again, it's still the same formula. I don't know why I said it like that. It's kind of like how a lot of sort of Anglophone tourists speak to people in other languages. They just slow down and be loud and assume that if you're loud and slow in English, people will understand you. That's not true, and don't do that. If the person has no idea what English is, you can't just say, it is the same formula. They don't look at you and go, yeah, well, still, I don't know what those words mean. Darmok and Jalad at Tanagra. So it's the same formula. We've just subbed in other things. Any questions I can answer at this point? God, I hate sitting still. I'm not totally psyched about getting back face to face, but am I ever psyched about not sitting in a chair doing my job? I hate it. I used to get a lot of my report cards when I was a kid. David is very fidgety and tends to take over group work. You'd never guess that, eh? Okay. If the variances aren't equal, they're never going to be equal. And let's get a rule of thumb. If one variance isn't, say, 4 times bigger than another one, that's a good rule. Let's use that as a rule. Things change. And in fact, generally, you probably would just do what's called pooling the variance anyway. But you know what? If it's less than about 4 times, maybe even 4 times. Yeah, let's go with 4. If it's less than, say, 4 times, if this one's less than 4 times bigger than this one, sorry, where are we here? This one and this one. If they're less than 4 times different than each other, frankly, it won't matter. But if they are, you should do this procedure here. By the way, there are ways to test for if one variance is equal to the other. If you want to be really conservative and you do a quick test, and you can see it if you do this on SPSS, you'll see it'll say equal variance is assumed, and then it'll say equal variance, and then it'll say variances are different, and it uses what's called the pooled variance, which is what we have here, which is one of these. What we're doing again is we're taking each variance and we're pooling them together. We're just getting an estimate of the two things together. So it's n sub 1 minus 1 times s squared sub 1 plus n2 minus 1 times s squared sub 2, and then it's plus n1 plus n2 minus 2 on the bottom. And then we're going to put that, the pooled variance. So we're going to say x bar sub 2 minus x bar sub 1 divided by the square root of the following quantity, s squared sub p, that thing we calculated, over n1 plus s squared sub p over n2. Doing this by hand is not horrible. It's just there's a lot of places to make mechanical errors. We're starting to get to the point now where using a computer or at least a calculator, but probably using SPSS, for example, to do this is a better approach. By the way, there are 3 videos just posted on my YouTube channel and also at davebrodbeck.com on how to do all these different t-tests using SPSS. So I encourage you to look at that and get a feel for playing around. Maybe make up a couple data sets and just play with it. just to get, again, more comfortable. And I've seen most of the first assignment, and most of you are pretty comfortable using SPSS or whatever other piece of software you want to use. So here we go. This is good. Where are we here? Yep. So how many degrees of freedom do we have? Anybody, anyone? How many degrees of freedom do we have in one of these 2 sample t-tests? Well, how many observations do we have? Let's start there. N1 plus N2. How many values have we fixed? Oh, we've estimated 2 variances. Yeah. So what we're going to do, so our variance is going to be, sorry, our degrees of freedom are going to be N sub 1 plus N sub 2 minus 2. So degrees of freedom aren't always N minus 1. Oh, somebody probably said that in the chat and I miss it because I missed the chat. Yes, I do. But yes, Chloe is correct. 2. Thank you. I'm going to put the chat over here. I miss it because, again, speaking of bad vision, I missed the chat. Let's put it here. So if anybody says anything else, I'll notice that it's there. All right. I'm in front of 2 24-inch monitors and it's still not, this is a non-trivial task for me. All right. Anyway, by the way, I hope you all enjoyed the new waiting room picture of our podcasting studios in our house. All right. N1 plus N2 minus 2. That's going to be our degrees of freedom. Assumptions for a t-test. Any t-test. A simple random sample. Yeah, we never have that. Like practically we don't. Do we have it? Do we assume it? Yes. Do we have it? Never. Do you think when people do, like, you know, many of you are, well, you're all, the vast majority of you, at least I think maybe a couple of you aren't honor psych majors, but the vast majority of you are. You've all taken intro psych. Do you remember in intro psych what you had to do, or you didn't have to do, were strongly encouraged to participate in experiments? And then there's the thesis conference, which I encourage you all this year to go to. Do you think the people in those experiments are randomly selected from all the population of humans? Let's count the ways that our intro psych students are not the same as the general population. Well, there's more women than men. So that's not true because there's pretty much a 50-50 sex ratio in the population. Let's see. They're pretty white. Well, they're, you know, and not everybody's white. It's in the world. There's a real lack of people from Africa right, in our intro psych classes in our university, because it's not a microcosm of the population of humans. So it's not really a random sample of humans. It's not even a random sample, is it? Are you randomly selected and you have to go to the experiment? No, of course not. You know what? It doesn't really matter that much. The math wants it to be a random sample, but you can simulate non-random samples and find out that the math works just fine. So while this is an assumption, we don't worry too much about it. And now this one we worry about: independence of observations. So if you know my score, that means you don't know anything about Evan's score or Chloe's score or Kaylin's score, anybody else in the class. You don't know their score based on knowing my score. You're saying, wait, Dave, what about that repeated measures thing? Yeah, but the difference between my score before and after, or between a pair, is not affected by the difference between other scores. So those scores themselves are still independent. So observations have to be independent. This is exceedingly important, and you cannot violate that assumption. That messes up the math to the point of it collapses and stops working. Are there ways to deal with this? Yes. To violation of that assumption? Yes, there are. Of course. But not using a t-test. Use a different kind of test. Homogeneity of variance. I talked before about, are variances the same or different? Would we use pooled variance or not? There's a rule of thumb that people say oftentimes that is one 4 times bigger than the other. And if they aren't, you're probably fine. And 4 times bigger is not homogeneous. They're heterogeneous. They're very different, right? But again, in practicality, it's this, you can't violate this too badly like you can with simple random sample. You can't violate independence of observations at all. You can violate simple random sample to the point of being literally ridiculous, like getting people who sign up for your intro psych to be in your experiment. That doesn't change the math. I'm not talking about how representative they are of a population. I'm talking about, is it randomly sampled? The answer here is no. Homogeneity of variance, we can violate this up to a point. This is why I talked about that pooled variance approach, because frankly, most times people will do that. One thing that you can get when you have variances that are different is you can use pooled variance. The other thing you can use is something called partial degrees of freedom. And I don't know how to do that math. Well, I do, but it's not easy math by hand. It involves matrix algebra, which I hate. Like I really hate matrix algebra. It almost made me quit graduate school. So yeah, so we're not going to talk about that. And most of the time people don't use the partial degrees of freedom tests. You will see them when you do SPSS or any other stats software. It'll give you a thing with partial degrees of freedom. You're going to find that usually that 99% of the time, that result, is it significant or not, will agree with when you just use pooled variance. Okay. Questions about this stuff, about t-tests? Now we've done, this is basically a month of intro stats in 47 minutes so far. So.
Would you be able to give us, sorry, would you be able to give us an example using the latest formula, please?
Yeah.
Thank you.
So using the 2 sample t-test, right?
Yes.
Okay. So something like, so let's see, this may be a bit of a, this may be kind of fun because I'll be doing this on the fly. Let's see how well I can make up examples. Okay, first I got to go share and I got to go to whiteboard. Okay, so we got 2 groups and we're going to compare 2 groups on some task, whatever the heck the task is. Let's say they're how well they do on tests, on the same test, and one group has been taught this way over internet, and the other group is being taught face to face. That's actually an interesting question, right? So let's see, we have 2 groups. We need 2 means. And we're going to say this is on, so we're going to say the percentages. So group 1 is the, I'm going to say they got 75. And group 2 gets, ooh, we lost somebody, or somebody's just joining in, one or the other. Let's let you, why is that? Okay, there you go. And group 2 has 70. Okay, now the variances for these 2 groups are going to be the same, not the same. We're going to make them, I'm just trying to make the arithmetic a little bit easy. It's hard to do this off the top of my head, but I'm going to say that S squared sub 1 for group 1 and for group 2, we're going to make them 25 and let's see, 15. And we have how many subjects in each group? We're going to make the math easy again, and we're going to say 5 and 5. Okay, so we have 2 groups now. I think I might have just yelled when I said okay. I apologize. Okay, it's a problem having a good mic. So let me just move my keyboard out of the way so I can easily do this here and not wreck anything. All right, so our formula then is 70 equals that minus that over the square root of S squared. Sorry, well, let's just big, that's fine. Okay, so we've got x bar 1 minus x bar 2, and I did s squared sub 2 over n2 plus s squared sub 1 over n1. divided by, so the square root, right? Okay. So what we would have in this case then is 75 minus 70, so that's 5, all over the square root of, let's say, s squared, I said was 25 over 5 plus 15 over 5. So that's going to equal 5 over, let's see, 25 over 5 is 5, plus 15 over 5 is 3 over 8. So over the square root of 8. What's the square root of 8? It's not quite 3, so it's 2.7 something. Alexa, what's the square root of 8?
The square root of 8 is 2.8284.
2.82. Good. Thank you, Alexa. 2.82. So I gotta have to erase some stuff here. So let's erase some stuff here. So good. So it's 2.82. I'm gonna have to ask the machine again for some help. So we've got now 5 over 2.82. So let's ask the magic thing again. Alexa, what's 5 divided by 2.82?
5 divided by 2.82 is approximately 1.773.
1.773. Very good. 1.773. Okay, so the obtained value we have for our t-test is 1.773. Now we have to know what the critical value we have to use to find to exceed that. And why isn't my stats book sitting here? Well, I'll just Google it, damn it. So how many degrees of freedom do we have in this experiment, this fake experiment we've set up? Remember, N2 was 5 and N1 was 5. So what's our degrees of freedom? 8? 8, correct. So it's 8. So let's look up what the critical value is for 8 degrees of freedom. I don't have the t-table memorized, and I don't think my magic speaker that's spying on my every move has a t value. Let's see if it does. That would be interesting, right? Alexa, what's the critical value of t with 8 degrees of freedom?
Here's something I found on the web.
Okay, it doesn't know.
According to reference.com, tea is a good source of natural antioxidants.
Alexa, cancel. Okay, so t equals, so it's t with 8 degrees of freedom. Let's look that up. Let's look up t with 8 degrees of freedom. So t, critical t, 8 degrees of freedom. And we look over here. T, oh, look, it's obviously somewhere I've been before because I found a purple link when I looked up t-tables. T with 8 degrees of freedom. And I'm going to look this up. Two-tailed 0.05 with, there we go, 8 degrees of freedom is 2.31. So the critical value is 2.31. Our obtained value is, so let's just, so this is, I am. So 1.73 is actually less than the critical value, which was, what did I say, 2.83? So in this case, we would not reject HO. We don't reject because our obtained value is less than our critical value. So that's what we end up doing. We say, oh, there's no effect. There's no difference between the groups, whatever, what have you. Okay, so that's basically how you go through that. And if you do the thing with the pooled variance, all it involves is a bunch of extra arithmetic of doing, n1 minus 1 times s squared 1 plus n2 minus 1 times s squared sub 2 plus divided by n1 plus n2 minus 2. And then you would put you would have the pooled variance going here instead of the actual variances. But I just did this because I didn't feel like doing a whole extra set of just basically arithmetic, right? Okay, I'm just going to take that, How do I stop this? Well, that's really annoying. There we go. Okay. So that's basically how you go through these things. They're really not, it's stuff I know you've all done before, because, well, many of you I taught. The chat again. See, again, I missed the chat. Thank you. Oh, thank you. You're very welcome, Isabella. We also found out that my digital assistant thing in my house does not have an internal tea table, which I guess shouldn't surprise me. Here's a thing I found on a web about tea. All right. Other questions?
Just when you're doing that, like when you do the formulas and you get the answers, do you want
Yep.
us to keep 2 decimal points or 3?
Oh, I'm sorry. I missed the last thing you said. Do you want to keep how many points?
Sorry, do you want us to keep 2 decimal points or 3?
Oh, I don't care.
Oh,
Two is probably reasonable. Because most your tables would go up to 2 decimal places. Yeah. So 1 isn't going to be enough. 2 is probably fine. We could get into a whole discussion of significant digits that I'm not going to get into, but I would say 2 is pretty standard. You'll see that in a paper. Think about this when you're reading an article. You'll see the statistical stuff goes to 2 decimal places always. It doesn't go to 3 typically. It typically goes to 2, and your tables go to 2. Now, sometimes SPSS will give you ridiculous numbers of decimal places. So when you look at the probability, it might say 0.00036. It's like, well, you don't need that. That's less than 0.05. I'm fine. Right? 0.00036. What's that? 36 100,000ths? I think, or they say it's 36 10,000ths, I guess. 000. No, it's 36 100,000ths. That's nothing. It's basically nothing. You don't really need that kind of level of detail, but you get it from the software. And that's a real issue. In fact, people are slaves to their software, to statistical software. The best and worst thing that happened to statistics was the fact that computers came along and made doing statistics easier. And it's great because it makes doing it easier. That's always good. But people then start lifting things out of statistics outputs and they don't really know what they mean. And that's the problem. That's why this course exists. Other questions? Because we're actually, I'm done everything I wanted to get done today. We can be done early. I'm perfectly willing, however, to hang out a little bit. And if you have any other questions.
I have a question or just a clarification.
Sure, go ahead, Clay.
So we did not we did not reject the null hypothesis on the last example that you gave because it was smaller than the critical value. And if it was larger, then we would reject it, which would mean that it had significant difference. Yeah.
Yeah, if it was bigger than the critical value, we'd say it was significantly different. If it's not, it's not, and we don't reject. Yeah, that's all it is. Thank you for checking though, because people do make mistakes and that's an easy place to make a silly mistake, right? So when you're doing an example of some sort on a quiz or a test or whatever, you don't want to make a mistake that way because it's an easy mistake to not make. So thank you for asking, actually. Appreciate it. Other questions, comments, clarifications, other things that start with a K. Kudos. Cranberries. Don't give me cranberry. I hate cranberries. It's one of the worst fruits ever. They should be good, right? You look at them, they're bright red.
Is the quiz on Tuesday on a specific chapter or just anything we've covered?
The stuff that we've done since the last quiz. So it's t-tests and what was the other, what did we do the other day? It all runs together. So it's t-tests, it's hypothesis testing, that kind of thing. Yeah. Yep. Okay, that's all. That's typically the way the quizzes are going to work. There will be times when I look at results of other quizzes and I say they keep making the same mistake. I'm going to keep asking them all till they get it. Now, this doesn't work so much when we do the online quizzes as our first two are, but once we're in person, the quizzes are going to have definitions on them too, very quick definitions. It'll be like mean, and you would write X bar divided by, or some of the X's divided by N, and that's fine. I remember one year I had the word population. as a definition, and people kept getting it wrong. And I kept putting it on every quiz until we got to like quiz 6. And I actually had it in capital letters, population, because I wanted everybody to know it was all the cases of interest. And people were still saying, what's the total number of people in a city? And they weren't saying that. Well, but again, this isn't in this course. This was in 21-26. I did see that in that course. So so sometimes I'll do that, but right now, no, it'll, so far, they're just, things from since the last quiz. Yeah. Other questions? Okay, so I'm gonna do.
Can you explain the difference between two tail and one tail?
Yeah, sure. Good question. So let me again pull up the old blackboard of sorts, which is actually not a blackboard as much as it is a whiteboard. Okay, there it comes. So if you have two groups and you want to see that one group is bigger than another, so that maybe, let me again move my keyboard out of the way. So we have, I'm going to try something here. Can I write? Yes, let's try it like that. So if I have two groups and I want to know if one group is bigger than the other, the test I'm going to do, right, is always going to be that's what I'm interested in. Right? That's the top of the T formula. Now the HO in this case is this is equal to that. So that doesn't change if it's one-tailed or two-tailed. But the HA is, it could be this. mu1 is not equal to mu2. There's a lot of cases where, in fact, and I said before, the majority of the time, I think that's the appropriate hypothesis, this one here. And I think it's the appropriate hypothesis because you're being conservative. You're saying just that mu1 doesn't equal mu2. But what if you have a case where it's impossible for mu1 to be bigger than mu2? Or for mu2 to be bigger than mu1, whatever. So in this case, your hypothesis now becomes, let's say mu1 is bigger than mu2. So if we were to look at the distribution of possible differences, a distribution of differences, okay? If it could be, if this is our hypothesis here, the non-directional or I guess let's go, or bidirectional hypothesis, there's a possibility the result could be here and a possibility the result could be here. And if we want to get a 0.05 level for alpha, we'd have 0.025 in that shaded area and 0.025 in that shaded area. But let's say we have a case where it's impossible that people could do more poorly. And here is an example. If we were teaching people something that they knew nothing about, so what's something that I don't know, what's something that let's say it's kids in their first day of science class. So they've never learned anything about, I don't know, atoms. And you tell them about protons and electrons and neutrons. So you're starting really slow, straightforward. You're just using that. Okay. We would never expect if we gave one group, didn't teach one group had anything about protons, electrons, and neutrons, and we taught the other group of, let's say they're 10-year-olds, about protons, neutrons, and electrons. Well, the group that learned something is going to do better. They might do the same because you're a really lousy teacher, but they're probably going to do better. They're not going to do worse because the kids who know nothing know nothing. They may have heard the word atom when mom and dad are watching Star Trek or proton, and they confuse it with photon torpedoes. So, okay, in that case, I think we could use this directional hypothesis that the group that learned a bit about atoms will be better than the group that didn't learn. And in that case, we don't have what's called our rejection region in both tails of the distribution. So that's here and here. Instead, we have our rejection region, and let's maybe change color. How do I, oh, there it is, yep. Let's go with that color, let's go with blue. So now our rejection region, we're gonna take this 0.025 and put it all over here. And that's 0.05. So now we have the same level of significance. We still care about a 5% chance, a 5% chance of being wrong, of saying that the null hypothesis is true. But it's all in one side. So we're going to have to exceed a somewhat smaller number with our significance test. So if you look on a t-table, you'll see that sometimes it'll be point, it'll be, let's say it's 1.3 or 1.7 or whatever, but if it's two-tailed, it's 1.3, something to that effect. So it's easier to find significance because there's more, because the number you're trying to exceed is smaller. That's all that means. But like I said, I think that it's pretty rare when I can make a case that I know one group that it can't be smaller than another. That's me. I'm very, what's what I'm looking for? Very conservative with statistics. Not everybody thinks the same way I do, which is probably good because we need fewer people like me. Does that help? Yeah. Excellent.
Yeah, it does
Cool.
help. Thank you.
Thanks, man. We have I see something else here. Let's see. No, that looks like the chat is good. Okay, good. Anything here? Anything else? Any other questions or comments or other words that go or don't? I mean, you could use other phonemes. All right. Somebody's tired.
I have
All
a
right.
quick question.
Go ahead, Chloe. You're awesome.
Not related to the topic, but I was just curious. You've taught this course many times. Is there like for the exam season, is there usually like a day that it's put on?
That depends on everybody else's schedule and stuff. Yeah. No, there's
Okay,
no.
so it's not like a set
no.
time. Okay.
No. You'll know
Okay.
that by the break, I would imagine, just because that's typically what they do. But yeah, I have no idea. Yeah. But
Sounds
yeah,
good.
I have taught this course many times at 3 different universities. It's basic. Everybody has one of these courses. So I taught it once when I was a grad student. The first course I ever taught was this. And it's been a long time. The beautiful thing about this, unlike most things in science, is statistics at this level, it doesn't change, man. So I don't really have to rework doing this class too much, just mostly teaching methods, not the actual content, which makes it a little bit easier to teach in some respects. Other questions?
On a test, would you want us to explain why we don't use the previous formulas and why we use like the other one?
If you think that helps answer the question. I mean, I can't answer that because it usually no. No, usually I wouldn't want something like that because I don't know that it would help answer the question. Are there cases where that would help answer the question? I guess possibly.
Okay, thank you.
Yeah, it's a fine question, Isabella. Not really. Yeah. Anything else? It's funny, we've got literally 3 of us doing this right now all at the same time in my house. All right. On that note,